this uh, the quantum states. The quantum states of an electron. Quantum state of an electron. At the same time, we are going to discuss how this notations, spectral notations for each quantum states are used or are defined or how are being used, and based upon that, for a given atom or given electron in an atom, how to write its quantum state in different terminology. So what is the terminology, that also we are going to discuss in brief with some specific examples. And as I said yesterday, in the single valence electron system, now the electron in this last orbit, the free not free but unpaired electron, that electron has two different types of angular momentum, and that is called as spin angular momentum as well as the orbital angular momentum. And because of that, this electron has certain magnetic properties, and the atom itself gets these magnetic properties or its magnetic properties because of that single unpaired electron. So that type of system is called as one valence electron system. And now in one valence electron system, now whatever when we go for its detailed study of the spectrum of such type of one valence electron system, you will find that spectrum of such element. The example of that specific example, if I can give, that is the example of sodium. So certain quantum states are doublet, so certain spectral lines are found to be doublet. So sodium D1 line and sodium D2 line, that is the best example of doublet. Why these doublets are occurring, this can be understood on the basis of this interaction, which is called as spin orbit interaction. So we will start that derivation today. It is lengthy derivation. It will require at least 2 lectures for that, but today we will see the primary things about that. Now, as we have already discussed, what is the quantum state of an electron? Now we have been introduced to 4 different types of quantum numbers. So first one is principal quantum number, second is the orbital quantum number, third is magnetic quantum number, which is given by ml, and fourth is the spin magnetic quantum number or spin quantum number. And these 4 quantum numbers are the address tags. Just like an address, we require some district, state, then your location, then your house number, your name, etc. Likewise, these quantum numbers are required to specify the position of an electron inside an atom, and based upon that, we have already seen this type of the Pauli's exclusion principle and so on. Now, this particular numbers define a state or the location or the situation or the address of an electron inside an atom, and that is called as a quantum state. So very small definition, we will write in brief and then we will move further. Okay, now right here, every electron in an atom every electron in an atom, just a minute, I am call from the principle. So every electron in an atom has its own and unique set of 4 quantum numbers. Okay, that is what we already discussed. N, L, Ml and Ms. So this is every electron possesses such a unique and own set of quantum numbers. So this set of quantum numbers, okay, I write it short, quantum numbers which specify the state of an electron, in an atom, just like as we have seen address. Your address specifies your state. Just like what? The set of the 4 quantum numbers, unique set of 4 quantum numbers specify the state of an electron inside that atom. Okay, and atom, and this is called as the quantum state. This is called as the quantum state. Quantum state, because address of that quantum state is specified by these 4 quantum numbers n, l, ml and ms. So this is required to specify any of the quantum state or state of an electron inside an atom, which is called as a quantum state. Okay. Now there are several examples which we have already seen on these quantum states and so on. So one such example I will take here. Z is equal to 8, that is oxygen atom. Oxygen atom, and as we have seen yesterday, we can write its configuration as electronic configuration 1s2, 2s2 and 2p4. Okay, so 2 plus 2 plus 4 plus 4 is 8. So its electronic configuration, if we go for this, it will look like this. This is first cell, second cell is again completely filled, and in the third cell, okay, I am drawing this close. So here now these are the 2 electrons, one up and down, one up and one up. So this way, so these electrons will get accumulated accordingly. And how many states are there? There are 2 states here, there are 2 states here, and there are 4 states here. These 2, 1 and 1. So such type of 8 quantum states are there. 8 quantum states are there. We can mention their names, we can mention their numbers. So what happens in 1s2 state? So electron in this 1s2 state has n equal to 1, l is equal to 0, ms is equal to 0, and ml is equal to 0, and ms is equal to plus half for first electron. For second electron in the 1s2, it has n equal to 1, l equal to 0, ml is equal to 0, and ms is equal to minus half. Likewise, for each electron we can specify the quantum state, and that's how there will be in all such 8 quantum states are available for a new atom, that is called as oxygen atom. And likewise, for any of the other element or the atom, once I know the number of electrons there, we can write or we can go for its electronic configuration, and based upon that electronic configuration, lot many things can be understood. Actually, that is what we are going to discuss next thing, that is called as spectral notations of quantum states. So in spectroscopy, these quantum states are specified by some other different types of notations. We have to learn them. Give a next title, spectral notations. Spectral notations of quantum state. Spectral notation of quantum state. Spectral notations of quantum state. Now look here, when we go for this type of spectral notation of quantum states, what we require is, first it is required this small l as well as capital L, small s as well as capital S, and very many times we require this small j as well as capital J. Now this is what total angular momentum, this is the orbital angular momentum, and this is the spin. Okay, this is orbital, or that is because of the revolutionary motion, rotational motion of an electron inside an atom. This is because of spin or intrinsic spin motion, and because of this orbital and spin, the total angular momentum comes here, and this is called as the total angular momentum. So try to understand, this is for single electron. So whenever a single electron is there, I use usually small letters. When there are 2 electrons, then their orbital angular momentum gets added vectorially to get this capital L. Again, their spin angular momentum also gets added vectorially to get capital S. And there are 2 different schemes. Either I can add this capital L and capital S to get J, or I can get small l1 and small s1 and I can get J 1 for a particular electron, and adding all such electrons orbital this total angular momentum, I can get J. So these are the two different schemes. We are going to learn into details about that later on. But remember, for spectral notations of quantum numbers, we require these three types of numbers. So quantum numbers: orbital quantum number, spin quantum number, as well as the total quantum numbers too. So that is small j. This is quantum number. Small letters are quantum numbers, and capital letters are actual physical quantities. So this is orbital angular momentum. This is spin angular momentum, and this is the total angular momentum. And these are the quantum numbers. So this things must be known to us, and then we can go for discussion of following things: how the scheme is applied in atomic physics or in this atomic and molecular spectra to write these spectral notations for a given quantum states. Okay, so write in brief. For writing atomic states, it is necessary to know okay, capital L, okay, that is orbital angular momentum, then capital S, that is the spin angular momentum, and capital J, that is total angular momentum. J is total angular momentum of the atom. This should be known. Remember, capital J is vector sum of capital L bar and S bar. That is how J bar is given by L bar plus S bar. Okay, and this J satisfies the quantum condition. So this J bar takes values. Okay, J takes values from maximum values L plus S up to minimum value L minus S. So this addition, vector addition, is different than the scalar addition. That is to be known to us, and based upon that J can take different values. Now how orientation of this L and S is there, what is their angle between them, depending upon that J can take maximum values J L plus S and minimum values L minus S. So this entire scheme we will discuss further when we go for that. Okay, now here this capital L bar is given by summation of all Li bar. How many number of electrons are there? They are to be added together, orbital angular momentum, and then we will get capital L bar. Again, remember, this is a vector addition. Okay, everything is vector addition, so this is also a vector addition. Similarly, this capital S bar is also summation of Si. All individual electrons, their spins are to be added vectorially, and then we get this vector addition, that is S bar. So this is also vector addition, and once we get this L bar and S bar, we can add vectorially again to get this capital J bar. Okay, so that is to be understood. So then these are the two words we are coupling, going across. That is called as coupling. One is called as LS coupling, and second type of called as coupling is called as JJ coupling, small j, JJ coupling, dash coupling. Okay, more about this we will discuss later on, not today, not needed here. Now let's see something about this. The total angular momentum vector. J bar is characterized by the total angular momentum quantum number. The total angular momentum quantum number. number. Okay, this number is given by small j. This capital J bar is characterized by the total angular momentum quantum number small j. Okay, this J bar is also quantized. J bar is also quantized, and as per quantum mechanics, so as per QM, we get this J bar has satisfies this relation. J bar is given by root of small j into j plus 1 into h upon twice pi. We have already seen this. L bar is root of L into L plus 1 into h upon twice pi. Same is the case for S bar. Capital S bar is also given to be S into S plus 1 into h upon twice pi. This is called as quantum conditions or quantization. Same is applicable for this also J bar. So J bar is given by root of small j into j plus 1 into h upon twice pi, where small j is total angular momentum quantum number. Capital J is physical quantity. Small j is a number. So from this number I can get, now it's a number. Dimensions of this J bar will be dimensions of this h upon twice pi. Twice pi is again a number, but the dimensions of this angular momentum, that is the Planck's constant, this is same as the dimensions of the J bar. So J bar quantum mechanically is given by J bar is equal to root of j small j into j plus 1 into h upon twice pi, like this. So whatever we did in orbital and spin angular momentum, same is applicable here too. Okay, now actually in any atom, this capital J bar or total angular momentum of an atom is decided by the last unpaired electron. So actually in one valence electron system, last unpaired electron gives orbital angular momentum as well as spin angular momentum, and therefore the total angular momentum. This is one of the very important steps we have to write further. The total angular momentum the total angular momentum of an atom is decided by last unpaired electron in an atom. Okay, since as I said, we are discussing this one valence electron system, so whenever one of the electron remains unpaired in first cell, second cell, third cell, whatever it may be, doesn't matter, but that unpaired electron decides all the total angular momentum of any atom. This is to be remember here. The core or inside electrons do not contribute to the total angular momentum. So this is the characteristics of that particular element, which is decided by the last unpaired electron, and the core inside does not give any contribution to this total angular momentum, that is J bar. It doesn't give any contribution. And as I have already seen, the total number of allowed values of J bar, the total number of allowed values of J bar for given L bar and S bar are, okay, as we have written this, J bar is given by maximum, this is okay, modulus L bar plus S bar, then next value is L bar plus S bar minus 1 up to L bar minus S bar plus 1, and final value is where this is modulus, okay, every value is this modulus, final value is L bar minus S bar. So add them and subtract them. In between, all quantum values are allowed. So that is what the value of J bar. For example, if I have capital L is equal to 3 and capital S is equal to 3 by 2. capital L is equal to 3 and capital S is equal to 3 by 2. Okay, then see here, J bar will be equal to, make the addition of this L bar plus S bar, or L bar plus S bar, modulus of this, it will be 3 plus 3 by 2. So I can take 2 here, so it will be 2 into 3, 6, 6 plus 3 is 9, so maximum value is 9 by 2. Then similarly, last value J bar is equal to minus L bar minus S bar modulus. So this is 3 minus 3 by 2. So take this value here, again 2 here. Now this is 3 into 2 is 6 minus 3, and therefore it is 3 by 2 minimum value. Now can you understand in between? Now here if I go for in between, मतलब जो दोनों values थे, these values will be look like this. So it will be 5 by 2 and one more value is 7 by 2. Okay, difference between this is 1, difference here is again 1, difference here is again 1. So that is how J bar is equal to L bar plus S bar minus 1. J bar is equal to here also L bar minus S bar plus 1. So like this. So these combinations gives you the values of J bar to be 9 by 2 up to 3 by 2. So in between values you are not needed. Just try to understand, since it is quantized. So minimum value I'll get 3 by 2, maximum value I'll get 9 by 2, and it will be differ. So in between values will be differ by 1. So it is 5 by 2 minus 3 by 2 is 1, 7 by 2 minus 5 by 2 is 1, 9 by 2 minus 7 by 2 is also 1. So difference of any of these two is always found to be 1. So that is how J gets 4 values. Thus J bar has 4 values. J bar has 4 values. This is a vector addition. Try to understand, this is a vector addition. Okay, and remember there is one very specific simple rule once we understand this. Thus there are 4 values of J bar. 4 values of J bar in this specific example. In general, आता एकदा आपल्याला S bar माहित झाला की काय असतं. In general there are twice S plus 1, capital S, twice S plus 1 different values of J bar are possible. Twice S plus 1 different values of J bar are possible. Okay, and each J bar gives a separate atomic states, and that is what the quantum state are, the notations which we are going to write there. Okay, therefore this quantity twice S plus 1, it is called as multiplicity of the atomic state. This is called as multiplicity of atomic state. Okay, and therefore, okay, now for if capital S bar is equal to 0, then this twice S plus 1, it will be simply 1, because 2 into 0 is 0 plus 1 is 1, and this is called as a singlet energy level. For quantum state, singlet energy level. For S bar is equal to 1, this calculation gives me twice plus S plus 1 is equal to now 3. This is called as triplet energy state, 3. And if I go for S bar, capital S bar is 1/2. What will happen here? Then this twice S plus 1, so 2 into half is 1 plus 1, it will be 2, and this is called as a doublet energy level or energy state or quantum state. So singlet, triplet, doublet. that depends upon capital S bar value. Capital S bar is 0, the state is called as singlet state. Capital S bar is equal to half, the state is called as doublet. Capital S is equal to 1, then the state is called as triplet. You can go for higher values, and that type of multiplets also can be obtained. Okay. Now actual this particular things what we have discussed, that how they are to be used here, that will be discussed here. The atomic states are denoted by capital letters, okay, like capital S, capital P, D, F, G, etc. Okay. Now which corresponds to, that corresponds to value of capital L. So for capital L is equal to 0, it is A state. 1, it is P, capital P state. For 2, it is D state. 3 and 4. So for L values 0, it is capital A state. For capital L bar value or value 1, it is P state. 2 for D state. For 3, it is F state, and for 4, it is G states, and so on. Okay. And then remember, now there is one more scheme. The atomic state is denoted. Now how to denote this? Then the atomic state is denoted. Atomic state is denoted using a term symbol. Okay, and see how this term symbol is given. Here I have to write in the superscript twice S plus 1, that is multiplicity. Then this is the value of L later for that, and here I am supposed to write the value of this J bar. So twice S plus 1, that is the multiplicity, is written here. The angular momentum, orbital angular momentum, capital orbital angular momentum, or total angular orbital angular momentum, later for that is to be written there. And in the right corner, subscript, that is written to be small j. So that this is called as term symbol. So here, as I mentioned earlier, this is the multiplicity. This is the total angular momentum. And this is what we are representing as the later for total orbital angular momentum. We'll go for some specific examples, then you will understand very easily how this scheme is applied for any of the atomic state, provided we know its capital S bar, capital J bar, capital L bar, and based upon that we can go for separate states. Okay, and that's what S state, P state, D state, etc. Now let's consider one simple example. Consider hydrogen in ground state. Lowest energy state. Ground state or lowest energy state. Now the quantum numbers for such states can be written as, if we can write, n is least value, that is 1. L, okay, if n is equal to 1, L varies from 0 to n minus 1, that is simply 0. Then ml also varies for twice L plus 1. Now twice L plus 1 is 2 into 0 plus 1 is 1, and therefore only one value, that is 0. Minus L2 plus L including 0, that is this value, and this ms is equal to plus half. So this is the state here. Okay, now remember, since this is single electron, here I have n, L bar is equal to capital L is also equal to 0. Capital this ml is not case here. Then S is simply equal to 1/2, since single electron is there. So S is equal to 1/2. Therefore I can get J is equal to, so maximum is L plus S, and okay, no need to write every time bar there, and minimum is L minus S. So maximum is, so addition of this gives me simply 1/2, and L minus S. Okay, so that subtraction also gives me, okay, same value, it doesn't give another value. So addition and subtraction, since one of the component is, one of the component in this vector is 0, so there is only one possibility of addition, and that gives you J is equal to simply 1/2. Okay, and therefore I can write the state of this state of this particular system can written as okay, here 2s plus 1. Now multiplicity is twice s plus 1 is equal to 2 into 1/2 plus 1 is equal to 2. So this is doublet. Since L bar is equal to 0, so it is S state, and J is equal to 1/2. Therefore the quantum state of the ground state hydrogen ground state is written as doublet capital S half. So doublet capital S half. So how I have written the ground state of this particular hydrogen atom, that is doublet S half. So henceforth we are not supposed to call ground state of hydrogen atom. What we have to call doublet S 1/2, means that this particular electron or this atom for which we are discussing, it is in its ground state, or it is having the quantum numbers as mentioned above. So try to understand from quantum numbers how to write the quantum state which is given by this symbol. This is called as term symbol doublet S half. Okay, and it is read as, वाचायचं कसं किंवा म्हणायचं कसं. Okay, it is read as doublet S half. DOUBLET, doublet capital S half. Doublet S half. So this state written this way, read this way, लिहायचं असं आणि वाचायचं असं. It is doublet S half. Okay, so this superscript gives again, as we have seen, this is multiplicity. This is total angular momentum. And this S is equal S, this letter symbol S is for value of capital L is equal to 0. This is written to be this. Okay, now another one state will give here. Second example, if I have L is equal to 3, I am not writing bar every time there, and capital S is equal to half. Now let's see how they are added vectorially to give different values of J. Now as I said earlier, J bar or J will be equal to maximum value is L plus S, minimum value is L minus S. So 3 plus half is how much? Okay, 3 plus half, that gives me 2 here, 2 into 3 is 6, plus 1 is 7 by 2, and 3, okay, here this calculations I am writing further steps, and here this is I'll write this to be 3 minus half, that is going to be 2 by 5. 3 minus 2 is 2 by 5. Here 5 by 2. 3 into 2 is 6 minus 1, that is 5 by 2. Okay, and difference between 7 by 2 and 5 by 2 is 1. So there is a, according to quantum condition, these values are not possible in between. इथं आतमध्ये काहीच नाहीये. Only addition of this gives me 3 by 2 and subtraction gives me 5 by 2. They are separated by 1, and therefore only two values, only two J values, or that is doublet. That is a doublet. Only two J values, not doublet. Doublet नंतर म्हणते, not now. This is a only two J values are possible, and therefore if I go for multiplicity here, multiplicity is twice S plus 1 capital S, so it is 2 into 1/2 plus 1, therefore it is 2, or that is said to be doublet. Now it is said to be doublet. Okay, and therefore since L is equal to 3, let us use, we have to use here is a capital F, later to be used. used in term symbol. Term symbol is capital F. Okay, see here, L is equal to 0, S state, L is equal to 1, P state, L is equal to 2, that is D state, L is equal to 3, that is F state. So now this is F state, multiplicity is 2, and there are two J values are available. We have made one mistake here. 3 plus 1 half is 7 by 2, and 3 minus 1 half, 3 into 2 is 2, sorry, 3 into 2 is 6, minus 1 is 5 by 2. Only two J values are there. Okay, the two J values, that's right now. And therefore I'll get the states here is, one state is now this is doublet, then this is F state, one value is 7 by 2, and second is doublet F, this is 5 by 2. So the two quantum states here are doublet F 7 by 2 and doublet F 5 by 2. Two quantum states. In our book, in this example, they have given some different numbers. So try to understand this. Okay, and they have to be read as doublet F7 half. Okay, this is to be read as doublet F7 half, and this is to be read as doublet F 5 by 2. Here 5 halves. Doublet F5 by 2 or doublet F7 by 2. That's how. This is what a scheme used in atomic physics to write the quantum states based upon, we know that value of small l, small s, small j, or capital L. From that we can get capital L, capital S, and capital J. So once J is known, its multiplicity can be calculated, or S is known, its multiplicity can be calculated, and every J value represents a separate quantum state, or it represents a separate term symbol. Therefore I have written there are two term symbols in this example, as earlier we have seen. In case of ground state hydrogen atom, there is only one state, that is doublet S half state, whereas in this case of second example, we have seen there are two states, and both are the doublet, that is doublet F7 half and doublet F5 half, and as shown by this example. Okay, now at present this type of scheme may appears to be a bit difficult for you, difficult in the sense because it is not easy every time to remember all these things here, but as we go on for the next examples, several examples, we will try to understand these type of cases very easily. So how to go for this actual, आता जेव्हा जेव्हा आपण पुढच्या काही स्पेसिफिक एक्झाम्पल्सला जाऊया, तेव्हा हे सगळे वेक्टर कॅल्क्युलेशन्स कसे करायचे, जेव्हा आपण when we go for the actual diagrams, vector diagrams, when we draw for addition as well as for alignment or orientation of different types of vectors, we can come across. The scheme is very easy. Mathematically it may appear a bit difficult here, but when we go for diagrams, then it becomes very easy. How? That will be seen in the next few sessions. Okay, not here, it is not that. Now here, this is what the basic scheme used in atomic physics to represent this quantum state in, and that is called as the term symbol. Okay, now let's go next point, that is called as spin orbit interaction. Spin orbit interaction. This is a lengthy derivation. At least 2 to 3 lectures are required in the classroom. मध्ये त्याला 2 किंवा 3 लेक्चर्स लागतात. इथं मात्र आपल्याला आणखी थोडा जास्त वेळ लागणार आहे. So in today's discussion, we will just see a very basic primary things about this. Actually, these are the part of this that what you might have learned earlier in this electrodynamics. Because okay, so I'll just draw a simple crude picture. This is my nucleus, and this electron is revolving around this. Okay, so there has two motions. It has spin motion and it has, because of this motion, it has the orbital motion too. So this is velocity, this is orbital motion. And we have seen whenever there is orbital motion, there is some orbital angular momentum, and because of that there is some angular magnetic momentum. So magnetic field is associated with this angular momentum. Electron is a charged particle and it spins about its own axis, not physically, but we are assigning certain speed, quantum speed to that, and because of that also it gives rise to a certain magnetic field. So because of these two different types of motions, one is physical motion, second is the hypothetical motion, or that is not hypothetical but that is intrinsic motion, spin motion. So this electron possesses two different types of moments, okay, angular momentum, and that's why it possesses two different types of magnetic moments, that is called as spin magnetic moment and orbital magnetic moment. And these two spin, and these are actually magnetic fields, these two magnetic fields interact with each other in such a manner the energy level gets splitted, and that's why while observing its spectrum, instead of getting a single line, sometimes some energy levels get splitted, and therefore we get different number of singlets, doublets, sometimes triplets, etc. This singlet triplet observation is now associated with this spin orbit interaction. So spin motion and orbit motion gives rise to this certain magnetic moment, and whenever there are two magnetic fields which are having some different directions, they are supposed to have certain interaction, and because of this interaction, energy states or the energy values of a particular energy states goes on changing, and this change contributes to the fine structure in any one valence electron system. So that is what example we had already given. In case of sodium atom, that the last electron in this 1s2, there are 11 electrons, so 1s2, 2s2, 2p6 and 3s1. That electron in the 3s1 orbit, that electron plays a very vital role, important role in the spectrum as well as all the physical properties of that particular type of atom, and we have to go for such type of discussion again. Okay, so basically we'll write in brief. The lines of optical spectra, the lines of optical spectra of alkali atoms, for example sodium, okay, then what are the next, potassium, sodium, the series त्या गटामध्ये एलिमेंट्स कुठले आहेत, सोडियम आहे, पोटॅशियम आहे, के, अँड देर इज वन मोर एलिमेंट, मला वाटतं एनिवन रिमेंबर्स दिस, पुढचे जे एलिमेंट्स आहेत त्याच ग्रुपमधले सोडियम आहे, त्याच्यामध्ये शेवटच्या ऑर्बिटमध्ये एक इलेक्ट्रॉन शिल्लक आहे. विल गिव्ह दिस एक्झाम्पल्स लेटर ऑन. Alkali elements show fine structure splitting, fine structure splitting, which indicates that all energy levels okay, capital P, D, F, etc. are doublet, except for those small l is equal to 0, except for those small l is equal to 0. This is due to spin dash orbit interaction. This is due to spin orbit interaction acting on optically active electron, so last electron in the last orbit is called as optically active electron. Okay, So every motion, every different types of motion gives rise to a certain magnetic field, and these magnetic fields interact and they change the energy states a little bit, and that gives a rise to a doublet or the fine structure observed in all types of alkali metals. Okay, so this particular concept was discussed by, there are several scientists, Pauli, 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 then Darwin, not this Darwin, the Darwin theorem madla ha Darwin nave, Dirac, and one more name is Gordon. These are the name of the scientists who worked a lot on the basis of quantum mechanics for this model, vector 2 model, to introduce this concept of this spin orbit interaction, and that's what this is called as the spin orbit interaction we are going to discuss here. So let's write one definition here. The interaction energy, is nothing but the change in kinetic energy. So the spin orbit interaction gives change in kinetic energy of the system due to the precession. I don't know how many of you know this word of meaning of the word precession, of the electron around the field. Okay, I think this word precession, etc., this word etc. is a little bit difficult for you to understand what this precision means. Actually, already in chapter 1 we have talked something about this precision, but here in this case this precision requires a lot of much importance there. Okay, and before that we go for this all this spin orbit interaction, etc. We are supposed to treat the electron revolving around a nucleus. Okay, so one valence electron system, for example hydrogen atom. This electron is giving rise to a certain current because it is forming a loop, so that is forming current. Whenever there is a certain current, there has to be some magnetic field associated. That is called as Biot-Savart's law. We can use Ampere's law for that. So this particular law gives rise to a certain magnetic moment or magnetic field, and this electron which is revolving in this magnetic field, this electron undergoes a precession motion. So it is not revolving in the same orbit all the time. Orbit goes on changing time to time, and frequently it goes on changing. This change of orbit, because of the interaction between the magnetic field as well as the electric charge of that electron, this motion is called as precession motion. Okay, so I think more about this we will discuss in tomorrow's lecture, because this entire derivation it will be required at least 2 lectures. म्हणजे आपल्याला किमान 2 lectures लागतील. Once we sit here, once we start writing getting this derivation done, then up to end we will come across after each and every aspect or details of that. What is this spin orbit interaction, how it occurs, how to calculate this interaction energy. Here it requires a lot of knowledge of electrodynamics, it requires knowledge of quantum mechanics, it requires knowledge of mathematics as well as trigonometry too. So all these things are required here to understand this concept. Actually I could have given directly, that means in spin orbit interaction this is the expression for the energy change. I could have given this, but let's try to understand this right from the detail, how this spin orbit interaction is discussed by these people on the basis of a certain quantum mechanical principle, and based upon that how they have arrived to a final expression for that is called as term values. So once we get this particular term, how these terms are separated, then energy values are separated, and based upon that doublet, triplet, singlet, whatever different types of spectrums are possible. So this particular correct explanation can be given by this derivation. So I suppose we will go for this derivation in the next lecture when we are going to meet once again. Okay, so my attempt will be that in this week we will try to finish this particular chapter. Once we go for this derivation of spin orbit interaction, we are directly going to discuss the spectrum of one valence electron system like sodium, potassium, etc. And whatever the spectrum described here by theory and the spectrum which is observed by experiment, if they are matching, then our theory is correct, the spin orbit interaction is correct. This can be proved very easily when we go for this spectrum of this sodium atom. Its electronic structure can be known. From that, its different types of energy levels are seen. This can be splitted, and based upon that, sodium D1 line, sodium D2 line, this type of fine structure of the sodium can be discussed very nicely. Okay, so today we'll stop here. You may have